Section 1.5 Derivative Techniques. Southwestern College, Professor Maria Olivas. Derivative techniques. Objectives. Use rules to more easily determine derivative functions. Apply derivatives to problems involving tangent lines. 1. Differentiation rules. First, some notation. These are all ways to write the derivative of y equal to f of x. We can write it as f prime of x. We can write it as dy over dx, the derivative of y taken with respect to x. We can write it as y prime. We can write it as d over dx of f of x, the derivative of f of x taken with respect to x. Computing derivative values through use of the definition of derivative, the limit we learned, can be extremely tedious and sometimes very difficult. There are several shortcuts that we can use to compute derivatives more easily. 1. The derivative of a constant. The derivative of c, where c represents a constant, is going to be equal to 0. For example, if we have something like y equal to 3 and we take this derivative of y with respect to x, it's going to be equal to 0. Or another example would be, if we have f of x is equal to pi, the derivative of f of x will be equal to 0. 2. The power rule. The derivative of x raised to the nth power is going to be equal to n times x raised to the n minus 1 power. Example, g of x equals x raised to the 8th power. G prime of x equals 8 times x raised to the 8 minus 1 power, which can be simplified to g prime of x equals 8 times x raised to the 7th power. I'm going to draw a vertical line segment here to separate this first example from the second example that I'm going to do next. So my second example for this power rule is going to be y equals the square root of x. The first thing I'm going to do is I'm going to rewrite that square root as a rational exponent. So it'll be y equals x raised to the 1/2 power. So dy dx will be equal to 1/2 x raised to the 1/2 minus 1 power. I'm going to erase the 1 and I'm going to write it as 2 over 2 so that we have a common denominator. So dy dx, the derivative of y taken with respect to x, is going to be equal to 1/2 x raised to the negative 1/2 power, which can also be written as 1 over 2 x raised to the 1/2 power. And I'm going to just lasso all the work I did for that example, shrink it, move it slightly to the left. And this can also be rewritten as 1 over 2 times the square root of x, or 1 over 2 radical x. 3. The constant multiple rule. The derivative of c times f of x. So the c that represents the constant, that can be factored out and written out in front of our derivative. We can write this as c times f prime of x. An example would be f of x equals 9x raised to the 5th power. So f prime of x would be equal to 9 times, and I'm going to take the derivative of x to the 5th, which will be 5 times x raised to the 5 minus 1 power. So f prime of x is equal to 45 times x raised to the 4th power. I'm going to draw a vertical line segment here separating the work that I did for my first example from my second example. My second example is y equals 7 over 3x raised to the 4th power. First, I would rewrite this function as 7/3 times x to the negative 4th power. So here, my 7/3 is going to represent the constant. I'm going to write that out in front, separated from my x to the negative 4. So it's going to be y prime is equal to 7/3 times -4, I'm going to write this as -4/1, times x raised to the -4 minus 1 power. Y prime is equal to -28/3 times x to the -5th power, which is equal to -28/3 times x to the 5th power. Number 4, the sum difference rule. The derivative of f of x plus or minus g of x. This is equal to f prime of x plus or minus g prime of x. The example here is going to be y equals 4x to the 5th minus 8x to the 3rd. So if we take the derivative of this function, we are going to get y prime equals 4 times 5 times x raised to the 4 minus 1 power minus 8 times 3 times x raised to the 3 minus 1 power. So y prime is equal to 20x cubed minus 24x squared. Putting these four rules together, we can differentiate many functions quickly and easily. Example 1. Find the derivative of each of the following. A. G of t equals 2 times t raised to the 3rd power minus 4 over t plus the cube root of t squared. I've drawn an arrow from this function to the right, and I have written out g of t in an alternate form. I have written g of t equals 2t raised to the 3rd power minus 4t raised to the -1 power plus t raised to the 2/3 power. So g prime of t is equal to 2 times 3t raised to the 3 minus 1 power minus 4 times -1 times t raised to the -1 minus 1 power plus 2/3 t raised to the 2/3 minus 1, but I'm going to erase the 1 and rewrite that as 3/3 so we have a common denominator. So g prime of t is equal to 6t squared plus 4t raised to the -2 power plus 2/3 t raised to the -1/3 power, and this can be written as 6t squared plus 4 over t squared plus 2 over 3 times the cube root of t. I'm going to go ahead and box in these two last answers that I said, because either one would be a perfectly fine way of writing your final answer. F. G of t is equal to 5t cubed minus 4 square roots of t over t squared. I'm going to rewrite this. So this is going to be equal to 5t cubed over t squared minus 4t raised to the 1/2 power over t squared. This is equal to 5t raised to the 3 minus 2 power minus 4t raised to the 1/2 minus 2 power if I use the quotient rule. Then we would have g of t is equal to 5t minus 4t raised to the -3/2 power, and g prime of t would be equal to 5 minus, I'm going to write this as 4/1 times -3/2 times t raised to the -3/2 minus 2/2 power. So g prime of t equals 5 plus 12/2 t raised to the -5/2 power, which can be simplified to g prime of t equals 5 plus 6t raised to the -5/2 power, or g prime of t equals 5 plus 6 over radical t raised to the 5th power. Either one of these last two answers, you could box either one in and they would be good answers, or you would want to make sure you read the instructions carefully to know how to write your final answer. G. m of v equals the quantity 7v plus 3 times the quantity v squared minus 9. I'm going to multiply out these two binomials to come up with a polynomial. I would come up with m of v is equal to 7v cubed minus 63v plus 3v squared minus 27. v prime of v is equal to 7 times 3v raised to the 3 minus 1 power minus 63 plus 3 times 2v raised to the 2 minus 1 power minus 0. So if we simplify here a little bit, we will end up with m prime of v is equal to 21v squared minus 63 plus 6v. And if I write it in descending order, it will be m prime of v is equal to 21v squared plus 6v minus 63. I'm going to go ahead and box that answer in. Applications. Find the equation of the line tangent to the graph of f of x equals negative x cubed plus 7x squared plus 5x minus 1 when x is equal to 1. In order to find the equation of a line, we need a point and we need the slope. Our point is going to be 1 comma f of 1. F of 1 is equal to negative times, open up a set of parentheses, 1, close the parentheses, raised to the third power, plus 7 times 1 squared, plus 5 times 1 minus 1. This is going to be equal to negative 1 plus 7 plus 5 minus 1, which is equal to 6 plus 5 minus 1, which equals 11 minus 1, which is equal to 10. So therefore our point will be at 1 comma 10. Now we need the slope. In order to find the slope, we will need to find the derivative, or f prime of 1. So f prime of x, I'm just going to draw a horizontal line here separating the work from finding f of 1 to finding f prime of x. F prime of x is going to be equal to negative 3x squared plus 14x plus 5, and f prime of 1 is equal to negative 3 times 1 squared plus 14 times 1 plus 5. So f prime of 1 is equal to negative 3 plus 14 plus 5, and f prime of 1 is equal to 11 plus 5, which is equal to 16. Therefore, f prime of 1 is equal to 16. That's our slope of our tangent line. I have drawn a vertical line segment to separate the work that I did from finding f of 1 and f prime of x and f prime of 1. On the left-hand side, I'm writing y minus y sub 1 equals m times x minus x sub 1. I've labeled my coordinates of my ordered pair as x sub 1, y sub 1, and my slope as m. I'm going to substitute, so I will get y minus 10 equals 16 times the quantity x minus 1. I will now distribute I will box in that answer that's in point slope form. This is a valid way to write your final answer. You could also write this in slope intercept form. If I were to write it in slope intercept form, I would distribute the 16. So it would be y minus 10 equals 16x minus 16. I would add 10 to both sides, and I would get y equals 16x minus 6. Number 3. Find where the curve, I'm now pointing an arrow pointing to the left at this equation in slope-intercept form, and I'm writing down the word slope-intercept form next to that equation. Number 3, find where the curve in number 2 has a horizontal tangent line. In order to find a horizontal tangent line, we need to, I am underlining the words a horizontal tangent line. In order to find a horizontal tangent line, I know that that's going to be where the derivative is equal to 0. So I have written down f prime of x equals 0. So I'm going to take my equation for f prime of x and I'm going to set it equal to 0. F prime of x is equal to negative 3x squared plus 14x plus 5. And I'm going to set it equal to 0. So I'm going to multiply the left-hand side of the equation and the right-hand side by a negative 1. So negative 1 times, open up a set of parentheses, negative 3x squared plus 14x plus 5, close the parentheses, equals 0 times negative 1. So if I distribute that negative 1 to this polynomial here, I will get 3x squared minus 14x minus 5 equals 0. Because this is a trinomial of the form ax squared plus bx plus c, I am going to factor. So this will give me the factors 3x plus 1 times the quantity x minus 5 equal to 0. I will now set each one of these factors equal to 0. So I will have 3x plus 1 equal to 0 and x minus 5 equal to 0. I'm drawing a vertical line segment. On the right-hand side of the vertical line segment, I'm going to continue solving each one of these equations. So I'm going to write down 3x plus 1 equals 0 and x minus 5 equals 0. I'm subtracting 1 from each side of the 3x plus 1 equals 0 equation. So I have 3x equals negative 1. Dividing by 3 to both sides, I get x equals negative 1/3. For the other equation, I will add 5 to both sides, and I will get x equals 5. Therefore, my solutions are going to be x equal to negative 1/3 and x equals 5. I'm going to box those two answers in. 2. Rates of change. Remember that the derivative is a function that describes the slope of a curve. The slope of a curve can also represent the rate of change of one quantity with respect to another. Example 4. If n of t represents the number of bacteria in a culture in terms of T, the temperature of the medium as measured in degrees Celsius. What does n prime of t represent, and what are the units? So let's go ahead here and try to explain this the best we can. I'm going to draw a coordinate plane. The vertical axis represents my y-axis. The horizontal axis represents my x-axis, but in this case, we're going to label it with the information that was provided for us in the problem. My y-axis is going to be labeled with n of t, which represents the number of bacteria in a culture in terms of t, and my x-axis is going to be labeled as t, which represents the temperature. So I'm going to write down the word temperature underneath t-axis in Celsius. And that, remember that that's also degrees Celsius. Next to the n of t axis, I'm going to write number of bacteria. I just went ahead and I drew a curve in quadrant 1 just to give me an idea here of what I'm looking for. I drew a point and I'm drawing a tangent line on that point. My curve looks like a curve that is increasing and is concave up. And my point, it has a tangent line drawn right at it, and it has a positive slope for that tangent line. So now thinking about n prime of t, which represents the slope of this tangent line, I'm going to need the y units over the x units, right? Or the n of t units over the t units. So n prime of t represents the rate of change of number of bacteria with respect to temperature. As for the units would be represented as number of bacteria over degrees Celsius. And that's going to be my answers for that problem. I'm going to go ahead and box in both of those answers. Example number 5. The temperature T of a person during an illness is given by T of T equal to negative 0.1 T squared plus 1.3 T plus 98.6. where T, capital T, is the temperature in degrees Fahrenheit and lowercase t is the time in days. A, find the rate of change of the temperature with respect to time. So I just want to repeat here that temperature T is going to be represented with an uppercase T and the time in days is represented with a lowercase t. So it's asking us here for find the rate of change. I have gone ahead and I have underlined T is the temperature in degrees Fahrenheit, T is the time in days. I have boxed in the function and I have circled the words the rate of change in problem A. This basically means I need to find the derivative. So once again here, I'm going to write down my function T of T is equal to negative 0.1 t squared plus 1.3 t plus 98.6. So now we're going to find T prime of T, the derivative of uppercase T with respect to lowercase t. It's going to be equal to negative 0.2 t plus 1.3. And I'm going to box that answer in. B, find the temperature at T equals 2 days. First, let me write down the original function. T of T is equal to negative 0.1 t squared plus 1.3 t plus 98.6. T of 2 is equal to negative 0.1 times 2 squared plus 1.3 times 2 plus 98.6. And that is going to simplify to T of 2 equals negative 0.1 times 4 plus 1.3 times 2 plus 98.6. T of 2 is equal to negative 0.4 plus 2.6 plus 98.6. So ultimately, the final answer, T of 2 equals 100.8 degrees Fahrenheit. C. Find the rate of change of the temperature with respect to time at T equals 2 days. T prime of T is going to equal negative 0.2 t plus 1.3. Now we are going to substitute T equal to 2. So it's going to be T prime of 2 is equal to negative 0.2 times 2 plus 1.3. So T prime of 2 equals 0.9 degrees Fahrenheit per day. And that's going to represent the rate of change of the temperature with respect to time at T equals 2 days.